So this question is very similar to the previous dilution problem, and I actually want to solve this one in two ways. And of course, the first way is perhaps less time efficient, but it really helps you understand sort of what's going on and what we're doing. And the second approach is a little formulaic in the sense that it's a little it's algorithmic in a way, but both work. So first I'll go to into the more exhaustive approach, and then I'll move my way towards talking about the formulaic approach. So we're looking at a problem here, and of course it has a part A and a part B. In the first part of the question, we're asked that a concentration of 300 milliliters of aqueous KCl, which is of course potassium chloride, solution was increased from 0.25 in terms of molarity to 0.75, also in terms of molarity. So the idea here is really, again, sort of to draw a picture and try to say, well, okay, we have a container, and this container, a concentration of 300 milliliters. So we'll just go ahead and sort of say that this is 300 milliliters. And of course, it says that the solution was increased from 0.25 to 0.75 in terms of molarity, which means that this 300 milliliters is actually referring to the first molarity before it was changed, which is 0.25 in terms of molarity, right? So these are sort of two characteristics that we have about the first solution in this case, which is of course KCl, right? So the second, as you can see, we're still talking about the same container, and we're still talking about the same solution, but we're sort of depicting this as before, right, and after. Okay, so it says that the molarity the concentration has actually increased. Of course, we have by evaporation. So the idea is that the water inside this particular this container has evaporated, leaving basically disturbing the ratio between water and solute, right? I mean, of course, solute, of course, will stay the same in either scenario, right? I mean, the amount of KCl doesn't change, but clearly with evaporation, the amount of water has changed. And that's an important point because what that does to the molarity is it in fact increases the molarity, the concentration. Because of course the proportion between solute and solvent, or water in this case, is sort of it has been changed in favor of the solute, right? Now there are basically, if you really look at what M means, right? M means moles per liter, right? So beforehand, where you had an X amount of KCl, which in this case, if we're given the molarity in this case was 0.25, we had 0.25 moles per liter of this solution. So if we scooped out a liter, we would have 0.25 moles. But now that the water has essentially evaporated, we have less solute for every, we have actually more solute for every liter because there are less, the quantity of water in its totality is less as compared to what it was before. So that distribution of particles, in this case a molecule, is sort of more potent, right? It is more apparent, more pertinent. And so really what's happened here is that the volume of water has decreased, and of course consequentially water has decreased, and so we're told that the volume we're told the molarity after the water has decreased is 0.75, which is of course consistent with our logic that if you take away the water, of course your concentration increases, right? Less water and more solute. Well, not more solute. The solute stays the same, but there's essentially that distribution is disturbed. So it's essentially asking us what is the new volume of the solution. So this is the volume before, which we're told is 300 milliliters. And we're asked for the volume after, right? What is the volume after? So, you'll sort of recognize that as we move forward, sort of trend in working these problems. And the trend is that one point to understand is that the moles will stay the same, right? Moles of the solute will stay the same. And the idea behind that is it doesn't matter if I dilute or add more water to the solution, or if I take away water from the solution. I should have the same amount of moles, right? Either way. Because if water evaporates, it doesn't take the molecule or molecules with it, right? I mean, if we have salt and we put it in water, when the water evaporates, you still have the salt. The salt doesn't evaporate. So the amount of moles of solute stays the same. It's consistent before and after. The volume has changed, and in fact, that's what we're being asked, which is of course the volume. And so that's an important fact, because whenever we're asked about concentration, immediately we're reminded, or we should be reminded, of a formula which says that the molarity is equal to moles of the solute over liter solution. So if you have how many liters, right? In either case, if you have how many liters the solution is in terms of its totality, and you had the moles in terms of, or you had the solute in terms of moles, you could get the molarity. But just like the Pythagorean theorem, sort of, if you have two of these guys, then you can get the third, and it doesn't matter which two you're talking about, so long as you have two known values. So, for this one here in the first situation, we have 300 milliliters, and we have 0.25 molarity. So we have volume. In other words, we have our liters, right? We could convert the ml to liters. And we also have molarity, which means we could solve for moles solute, right? We could do that. And the same thing applies here. If we had two of the known values, if we had two values which are known, we have molarity, but we don't have volume, right? But what if we had moles, right? If we had mole solute and molarity, which we already have, then we could in fact solve for liter solution. That would eventually help us understand the volume of what the solution is afterwards. So there's two ways you could go about it. So the first way is sort of a stoichiometry-based approach, and the second way is sort of a transposition-based approach. So the stoichiometry-based approach is sort of that so our digression is find how many moles of solute there are in either compound or either solution, knowing that it will be the same. So we start with what we know, and then we move our way forward. So if we start with the information that we're given of the previous solution, we can find how many moles there are in both scenarios. And the reason that is, why don't we start finding how many moles there are using this information? Well, the fact is that there's just not enough information. The information that we have in terms of abundance is presented in the first situation, right? We can use the information in the first situation to calculate moles, because we know that the moles amount will be the same in both cases. So we'll start with 300 milliliters of solution. This is, of course, of KCl. So as I move forward, I am sort of talking in terms of KCl and or potassium chloride. And then, of course, we can express this as liters. So 1,000 milliliters is equal to 1 liter. And as we move forward, we can use the molarity conversion factor that says for every 1 liter, and of course your liters would cancel out and your milliliters would cancel out, for every 1 liter, you have 0.25 moles of solute. And once you would do this, I mean, once you would sort of enter this into a calculator, you would multiply 300 by 0.25. And then, of course, you would divide by 1,000, and you'd get 0.075 in terms of moles, right? And you could use, again, you could use this approach, right? This is the stoichiometry-based approach. Or you could, if you wanted to, you could use the molarity-based approach, which essentially says that, you know, we have the molarity, we can convert the milliliters to liters and then use this to solve for mole solute. So that would look something like, you know, first let's go ahead and, you know, we would do, so we're solving for X moles, right? Mole solute divided by a liter amount. We're given milliliters. So if we take 300 milliliters and convert that to liters, knowing that 1,000 milliliters is 1 liter and 1 liter is 1,000 milliliters, these would cancel out. And let's see here. Yeah, so we'd essentially just be doing 300 divided by 1,000, which is 0.3. So we have 0.3 liters equals, right? So it equals, let's see, a molarity of 0.25. So X moles, if we were to divide both sides or multiply both sides by 0.3, equals 0.25 multiplied by 0.3. And so our amount of moles, 0.25 multiplied by 0.3, would essentially give us the same answer. As I said, this is just a different way to do the same thing, which is 0.075 in terms of moles. So you could really go either way, but you just need enough information. So, so now we know the moles, right? We have the moles. And we can go back to looking at the second scenario. I mean, of course, there are 0.075 moles in this case of solute, and there are 0.075 moles of solute in this case as well. Of course, the moles of solute won't change with evaporation. And so in order to calculate the volume, which was our original goal, we could plug in molarity, which we have, and mole solute, which we now have, and then solve for liter solution. So we know that it's 0.075 in terms of its moles of solute. And of course, our liter solution is what we're solving for, X liters. And of course, we have our molarity as well, which is 0.75. And if you were to solve for X, you would essentially be doing 0.075 divided by 0.75. And of course, again, plugging into a calculator or using some simple common sense for arithmetic here, you would get 0.1. Now, what is the unit in this case? Well, whenever you're using this formula, it's always in terms of liters, right? It always produces the end amount in terms of liters. So this is 0.1 liters. And if you wanted to express this as a volume in terms of milliliters, since that's what your original unit was expressed as, you would just have to say that, okay, well, 0.1 liters is equal to, or you could say that 1 liter is equal to 1,000 milliliters, your liters would cancel out, and you'd be left with 0.1 times 1,000, which would move the decimal place 3 places to the right, and so you'd be left with 100 milliliters. And that is your solution, and that's your volume, right? That's your volume for this guy after the evaporation took place. And then, of course, it's asking how much water was removed. Well, you started with 300 milliliters, and of course, you were left with 100 milliliters, which means 300 minus 100 in terms of milliliters is 200 milliliters. So 200 milliliters evaporated. Now, if this is too much, that's understandable. It's certainly less time efficient, but there is another way which allows you to circumvent having to go through the tedious nature of solving questions like this in this manner. And the solution here is to use the M1V1 formula. The M1V1 equals M2V2, and that itself is doing exactly what we've described, but in a more condensed manner, right? So let me just go ahead and leave it here, but the formula essentially says that the molarity in the first situation multiplied by the molarity or the volume of the concentration or of the solution in the first situation equals the molarity of the second situation multiplied by the volume in the second situation. So if you were to plug this in and then eventually solve for what you want, you would get a solid answer. So the molarity in the first situation is 300 milliliters, right? And of course, this one is also exclusively used for liters, just like this formula here, exclusively. Actually, no, I don't think this abides by that rule, but 300 milliliters, so if you have 300 milliliters is the first volume, well, I can't really use 300 milliliters, can I? So the molarity for the first situation, as we said before, was 0.25 times the volume, which is 300 milliliters, equals the molarity in the second situation, which is 0.75 multiplied by the molarity or the volume, in the second situation, which is what we're trying to find. So we'll leave that as a variable. So your volume 2, and of course your volume in your second situation, would be 0.25 multiplied by 300, but 300, that's of course in liters, milliliters. And then, of course, divided by 0.75. So you have 0.25 times 300. And, of course, if you were to divide that, you would get divide that by 0.75, you would get 100, right? In terms of milliliters. So whatever you put in, you get out. With this one, it just puts out liters, but with this one, whatever you put in, you get out, which is, of course, our answer. So this is sort of a more concise method at solving the same problem, but it's really convenient, right? You don't have to go through the whole process, but still, drawing it out really does help. And then, of course, after that, it's just a matter of understanding that you put in. Let's see here. Let's see. So you had 300 milliliters, and you were left with 100 milliliters. So how much was removed? Well, 200 milliliters, right? I mean, of course, you would minus them, and so that's essentially your answer.